We've seen what happens when a storm unleashes its awesome power. Now we investigate what triggers this mysterious phenomenon. What happens in the moments before lightning strikes? Our journey takes us to a city that's home to some of the world's most violent lightning storms, Darwin, in northern Australia. In just a few hours, Darwin can take as many as 1,600 strikes. This is the perfect place to investigate the mystery of what sparks a lightning bolt. An international team of scientists have come here to find out. Using radar and a fleet of aircraft, they're looking for the answer deep inside Darwin's monster storm clouds. A potent cocktail of heat and moist tropical air means these are no ordinary clouds. Called cumulonimbus, they can rise up to 12,000 meters at speeds of 100 kilometers an hour. "20 kilometers up, twice as high as a passenger jet, a modified former Russian spy plane flies above the storm, collecting data about the cloud below. Somewhere inside this cloud, lightning is preparing to strike. Understanding how has puzzled scientists for centuries, but they think the cloud acts as a giant electrical generator. Inside the cloud, tiny water droplets rise up, freeze, and fall back down as ice. On the way, they rub against each other, and electrically charged particles transfer from one to the other. The water and ice particles that were previously neutral are now positively or negatively charged. The negative particles sink to the bottom of the cloud, while the positive rise to the top, separating the positive and negative charges. When they reunite, lightning will strike. This is the theory. But the reality is even stranger. Air is not a good conductor, so electricity can't pass through it easily. To let the current through, the air's atomic structure must break apart. To do that takes millions or even billions of volts. Scientists have searched the skies for this huge electrical charge, but even in Darwin's massive storm clouds, it's never been found. In the story of lightning, there's a piece missing. It's a puzzle that fascinates physicist Joe Dwyer from Florida Institute of Technology.
With lightning, it's almost embarrassing. We've been studying lightning since the time of Franklin, and over 200 years, we still haven't answered the big questions. How does lightning work? How does it get started up in the thunderstorms? How does it propagate for miles through the air from way up there where it's initiated down to our feet?
Lightning is static electricity, and you can make it yourself at home.
Let me take my shoes off, and when I do, I'm going to rub my feet on the carpet. As I rub my feet, friction is going to separate electrical charge. Positive charge is going one way, negative charge the other. Now, when charges separate, they want to get back together. A large electric field can build up, and when this happens, you can get a spark. We think that something like that is going on inside a thundercloud when it makes lightning.
To send a current across this tiny distance takes up to 25,000 volts. But lightning bolts can be almost 200 kilometers long. Sending a current through this much air takes millions of volts, a massive electrical charge that so far scientists have failed to find.
You have to ask, well, where is the finger that's concentrating the charge to making the big fields to produce the spark? And we're having a really hard time figuring out what that finger is.
Thunderstorms are violent, and lightning is unpredictable. Getting close enough to make measurements is virtually impossible. Scientists can't get to the lightning. So at the University of Florida's International Center for Lightning Research, they bring the lightning to the scientists.
What we did is that we used rocket-triggered lightning. You can tell lightning where and when to strike.
Dwyer and the team fire a rocket into a charged storm cloud.
Ready to fire. Arming rocket. 5, 4, 3, 2, 1, fire.
It trails a copper wire that acts like a lightning conductor. Millions of volts of electricity race from the cloud to the ground. Dwyer uses data from this experiment to investigate how lightning can pass through several kilometers of air, and he looks for the answer in outer space. In a galaxy far away, a star explodes. Millions of microscopic electrically charged particles are forced out into space. These are known as cosmic rays. Traveling at nearly the speed of light, they race across millions of kilometers, taking millions of light years to reach Earth. Dwyer wondered if cosmic rays could explain how electricity travels through several kilometers of air. Billions of these rays bombard our planet every second. They're invisible and inaudible. But when a cosmic ray travels through the atmosphere, it momentarily rips apart the air's molecular structure. This produces X-rays, electromagnetic waves of radiation which can be measured. Could cosmic rays be the missing link in the story of lightning? It sounds like science fiction. Even the optimistic Dwyer thinks it's a long shot.
When we got our first triggered lightning and made our first X-ray measurements, I didn't even get around to looking at the data for a couple weeks, because I wasn't really expecting to see anything. When I sat down finally, there on the screen was an X-ray pulse right when the lightning occurred. I thought, well, what's the chance of that happening? I mean, right there at the same time. So we looked at the next stroke, and there was another pulse, even bigger. We looked at the next stroke, another pulse, and another pulse with the next stroke. Every time we looked, we saw a big burst of X-rays hitting our instrument at the exact time that lightning struck.
Dwyer believes this is a clue that something has changed the air's atomic structure. And he thinks that something could be cosmic rays.
For centuries, we've been laboring under the assumption that lightning is just a normal kind of discharge, like the finger touching the doorknob. We suddenly see now that this was wrong.
If Dwyer's right, when a cosmic ray hits a cloud, it causes a huge momentary surge in electricity, enough to create a spark, but too brief to be measured. The ray then hurtles on towards the ground. The superfast moving particles collide with air molecules and rip them apart. For a fraction of a second, the air becomes electrically conductive and provides a path down which the current can run. Now lightning can strike. A channel of negative electrical charge shoots from the bottom of a cloud. It heads towards the ground in rapid steps, each taking just 50 millionths of a second. As it gets closer, it begins to affect the ground below. Positive particles in the ground or in objects on it are drawn up towards their negative counterparts. A storm cloud can create dozens of these negative and positive channels. Most don't connect, but when they do, millions of volts of electricity race between the cloud and the ground. Lightning travels up as well as down. We see the lightning strike and we hear the air explode. In the following thousandths of a second, any remaining charge in the cloud surges up and down the channel, and the bolt may appear to flicker. Lightning really does strike more than once. And all this happens up to 8 million times every day, 100 times a second. Lightning is one of nature's most common phenomena, and if Joe Dwyer's theories are right, it's also one of the most incredible.
If these ideas are correct, then there may be a connection between the lightning that we see and a star exploding halfway across the galaxy in 1 million years ago.
We've traced the origins of a lightning bolt and investigated the terrible moment of impact. But now, in the moments after impact, our journey takes us into the bizarre world of fireballs, UFOs, and ghostly apparitions. It takes less than half a second to go from spark to strike. But what happens afterwards is much more enduring. A twilight world that seems to have been lifted straight from the pages of a science fiction comic. On the 19th of March, 1963, Eastern Airlines flight EA539 was traveling from New York to Washington. At 5 minutes past midnight, the plane encountered a storm. There was a loud bang and a bright flash. Then, seconds later, a glowing ball emerged from the pilot's cabin. The blue-white ball hovered above the aisle and floated slowly towards the back of the plane, where it vanished. Remarkably, the plane continued on, unharmed. This wasn't fantasy. It was fact. And it wasn't the first account of its kind. During World War II, pilots reported strange balls of light that seemed to follow their planes. US pilots named them Foo Fighters. For thousands of years, people have claimed to encounter fiery spheres like these as ghosts, messages from the gods, or UFOs. But there was something different about the Eastern Airlines account. The eyewitness wasn't an adrenaline-fueled fighter pilot or a medieval mystic. He was a professor at a prestigious British university. Suddenly, scientists sat up and began to take notice. One scientist who's been inspired by his own close encounter is nuclear physicist Dr. Graham Hubler.
I have seen ball lightning myself, so I know that it exists.
As a teenager, Hubler was on a date in a park in upstate New York. A storm broke out, and the couple took shelter in a bandstand.
And suddenly, off to our left, we're sitting there with open sides on the left and the front. Off to the left, we saw this ball approaching, ball of light. And, of course, we were terrified. What the heck was this? We didn't know what it was.
Slowly, the ball approached them.
It was about 30 yards away and coming slowly at us, just kind of drifting, ambling along, drifting along. And we're looking at this thing, and just we were both just paralyzed, actually.
To their horror, it entered the bandstand and rolled across the floor past their feet, emitting a strange sound.
The sound it was making was like a freshly struck match.
When it reached the other side of the bandstand, the ball leapt up and traveled out of the open side.
And it jumped right back up to about 6 feet off the ground and went out another 20, 30 feet out into the night, and then very quickly dropped to the ground and extinguished without a noise.
After this experience, Hubler developed a lifelong fascination with ball lightning. He has collected thousands of eyewitness accounts of multiple ball lightning, balls that fell from the sky, balls that exploded, hissed, spun, hovered, and jumped. Some ball lightning has even been seen to pass through solid objects without leaving a trace.
There is no good theory that exists that explains the features of ball lightning. Different theories can explain one or two of the features of ball lightning, but none really do a very good job of explaining it all.
One man who's examined all the evidence and investigated all the theories is physicist Mark Stenhoff.
There are probably almost as many theories of ball lightning as there have been scientists investigating it.
But there is one thing almost everyone agrees on. Ball lightning is probably plasma. Plasma is the commonest form of matter in the universe. The sun, fire, lightning, and the space between the stars are all plasma. It's not hard to make plasma. If you run a current through a gas, it will spontaneously emit light. But explaining how a fiery ball can materialize out of thin air has confounded scientists for centuries.
I think as soon as we see something we can't explain, particularly something as bizarre as that, we have a tendency to move outside our normal frames of reference and explain things using, if you like, rather supernatural kinds of explanations.
One of the more sensible theories is that ball lightning is produced by a rare phenomenon known as bead lightning. This footage shows a lightning bolt that appears to break into small beads. Some scientists argue that ball lightning is a plasma bead that's become separated from the bolt. But there's one problem with this theory. Eyewitnesses talk of balls lasting for minutes. These beads vanish in less than half a second.
We don't know of a way in which we could create a plasma in the atmosphere that's self-contained, that would survive for many seconds. A plasma would provide plenty of energy, but it wouldn't be able to survive for that period of time.
Is it in fact possible that ball lightning is the product of a lightning bolt? The story gets even stranger.
What was there?
Oh, yeah! You see it? Yes!
Already we'd ventured beyond the frontiers of science as we followed the journey of a lightning bolt. But this is just the beginning. Seconds after lightning strikes, high above the thundercloud, a strange new phenomenon appears. On the 6th of July, 1989, physicists from the University of Minnesota were testing a new low-light camera. They planned to use it for a high-altitude rocket experiment. They pointed the camera east, a random choice, at some stars and what looked like a distant thunderstorm. But when they played back the tape, something caught their attention. It was two funnel-shaped flashes of light that lasted for just a few thousandths of a second. The team estimated the flashes to be 30 kilometers above the clouds and an astonishing 20 kilometers tall. By pure chance, they had captured something new to science. From his research lab at Duke University in North Carolina, Professor Steve Kummer searches for these strange specters.
It's exciting to be part of something fundamentally new that no one else has seen before, and it's kind of a big surprise that these things have been there the whole time and nobody knew about it.
The twin pillars of light filmed by the physicists flickered above a thunderstorm in the distance. So what were they? Around the world, lightning scientists embarked on a hunt to find out. They didn't have to look far. Scientists reviewed hundreds of hours of video taken from the space shuttle. To their amazement, there were dozens of these strange apparitions, just waiting to be identified. Low-light cameras were trained on the skies. High-altitude aircraft flew above storms. Soon, there were thousands of recorded sightings.
Everybody was surprised by how common they in fact were. It's just one of those cases, once you know what you're looking for, all of a sudden you see a lot of them.
Scientists call them sprites because of their elusive, ghostly appearance and the way they seem to dance above thunderclouds in the night sky. They usually appear in groups of 2 or 3 and last less than 10,000ths of a second. Researchers from the University of Alaska Fairbanks calculate they occur in the middle atmosphere, 40 to 100 kilometers above the Earth, and can extend more than 50 kilometers across. Observations suggest sprites are related to lightning. But how? In a field in North Carolina, antennae pick up the radio signals produced by lightning. Steve Kummer uses these to listen to the radio noise made by individual lightning bolts. The equipment is so sensitive, he can detect lightning as it happens anywhere on Earth.
Every one of these individual pulses is one of those radio pulses from a lightning stroke somewhere in the globe.
Kummer uses this data to measure the size of each bolt. He matches this with sightings of sprites from other research stations, and he's noticed a pattern. Sprites occur in the fractions of a second after lightning strikes, but only after the most powerful lightning bolts. Kammer thinks this huge release of energy causes a disturbance in the atmosphere above. This high-speed footage, the most detailed film of a sprite ever shot, supports Kammer's theory. 70 kilometers up, the electrical charge momentarily increases, triggering a giant spark. Millions of electrically charged particles accelerate outwards at 10,000 kilometers per second.
Sprites tend to be about 40 miles high. The bottom here is maybe 25 miles, and the top is 60 or 65 miles.
Sprites come in many shapes and sizes, from the so-called A-bomb sprite, up to 100 kilometers in diameter, to a tall, skinny one about 1 kilometer wide and nicknamed the Diet Sprite. Five years after the first sprite was spotted, researchers from the University of Alaska Fairbanks were hunting for sprites high above a monster storm using a sensitive low-light camera. These researchers captured the first ever color images of sprites. This was a spectacular surprise. But with each new discovery came new questions. Scientists now wanted to know what caused this colorful display. Sprites are elusive, unpredictable, and almost impossible to observe at close range. So Earl Williams from MIT makes his own. He calls it Sprite in a Bottle.
What's your pressure now, Mike?
In a disused printing factory in Brockton, Massachusetts, Williams and his team use a plexiglass tube, an old steering wheel, and plenty of ingenuity to create their very own sprite. They recreate conditions in the middle atmosphere, 80 kilometers above the Earth.
It's the good sprite light. We start with a tube filled with air at atmospheric pressure, like the air in this room we're breathing. With vacuum pumps beneath the table, we pump the tube down to pressures corresponding to 50-mile altitude.
By running an electrical current through the tube, they create a magical light show. This is the same process that lights up Las Vegas. The neon gas in these tubes is invisible, but when a current is run through it, colored light is produced. Most of the gas in the atmosphere is nitrogen. When the air near the ground is hit with a current, it produces a dazzling white light. But if the pressure is changed, the color changes too. 80 kilometers up in the Earth's atmosphere, low pressure means nitrogen produces red light. But as the sprite stretches towards Earth and the air pressure increases under gravity, the color changes to purple and then blue. In the sky, sprites last less than 10,000ths of a second. But with the sprite in the bottle, Williams can study the forces that shape them in his own time. But even in the controlled conditions of the lab, the sprite is a volatile creature.
Okay, here I'm going to let in air.
Yeah, give me all you've got. Oh, that's a nice display.
Oh, that's neat.
I like that.
Nice flat discs. The sprites are very much alive, and as you can see, the patterns in the tube are very much alive, moving and writhing around and very unsteady. Oh, that's nice. Look at that.
The bottle lets Williams look deep inside the hidden world of sprites.
I've never seen that one before.
He's discovered that there may be even stranger phenomena waiting to be revealed. Sprite scientists have always expected the unexpected. But even they weren't prepared for this.
Oh, yeah. You see it? It was so beautiful.
In Puerto Rico in 2001, a jet of blue light shot from the top of a thundercloud and traveled 65 kilometers into the sky. Other sightings confirmed that this was not a sprite. It traveled up rather than down, and from the cloud, not the middle atmosphere. It was an entirely new species called a blue jet.
When I saw the videos, I was like, that's pretty spectacular. Wonder what those are. Blue jets are a mystery that nobody really knows what it takes to generate them.
And it didn't stop there. Next came an even rarer species, elves. A pulse from a lightning bolt triggers a horizontal halo of light about 100 kilometers above the Earth that spreads out rapidly to a diameter of up to 400 kilometers.
Just about everybody who has gone with a new instrument or to a new region of the world to look above thunderstorms for something new, they have found something new.
Sprites, blue jets, and elves make up a fantastic cast of characters. But are they as benign as their names suggest? What would it be like to encounter one at close range? These NASA test pilots are flying through a regular lightning storm. It's a bumpy ride, but it's a safe one. Modern aircraft are designed to cope with a direct strike. The current flows along and away from its frame and continues on to ground. A regular lightning bolt is about the width of a pencil, but these monsters can be up to 320 kilometers across. Aircraft can operate at the same altitude as blue jets, and spacecraft pass through the same altitude as sprites and elves. So what would it be like to fly through one of these mysterious phenomena?
That is one of the questions that we're trying to answer. What is happening inside them, and could that pose a threat to aircraft or anything else that spends time in those altitudes?
So far, no damage from a sprite, blue jet or elf has been reported. But while investigations continue, it remains a possibility. Lightning's weird offspring inhabit a world that we've only glimpsed, too high for balloon or aircraft samples, too low for satellites, and like the depths of the ocean, nobody knows what other creatures wait to be discovered.
Since there have been so many things discovered in the last 15 years, new things, it would not surprise me at all if there were more things out there waiting to be discovered.
We've followed a lightning bolt on its way through the Earth's atmosphere, from its devastating impact on the ground to its spectacular after effects above the clouds. Now our journey takes us into outer space as we discover why life as we know it could depend on lightning. During the Cold War, a top-secret U.S. operation with the codename Starfish Prime was attempting to investigate the effects of a nuclear war in space. On the 9th of July 1962, a 1.5 megaton nuclear warhead was detonated 400 kilometers above the Pacific Ocean. The explosion took place in an area of natural radiation called the Van Allen belts. Wrapped around the Earth like two giant donuts, they're full of deadly radioactive particles and a threat to astronauts and satellites. At NASA Goddard Space Flight Center near Washington, D.C., Jim Green monitors the radiation in the belts.
It's a very hazardous area because these particles are moving so fast they'll move through skin, through flesh, tissues, also through spacecraft, damaging delicate circuits and eventually leading to satellites that will no longer function in space.
Between the belts is an area with much less radiation called the safe slot. Commercial satellites are able to operate in the relative safety of this low radiation environment. In 1962, the Starfish Prime warhead sent a massive dose of radiation straight into the safe slot. Radiation levels soared, and satellites ceased to function. But just a few weeks later, the slot was once more free of radiation. NASA scientists were stunned. Something had recreated the safe slot. What was it?
We have been on the hunt to determine why that slot region is there ever since.
The evidence pointed to the sun. But in 2004, Green took a chance look at a magazine, and everything changed. An article on the distribution of lightning captured his attention.
The beautiful maps of lightning changed my concept of where lightning was actually being generated, drew my attention to the article immediately.
Green noticed that lightning exhibits exactly the same characteristics as the clearance of the safe slot. It occurs more over land than sea, more during the day than night, and more in the summer than the winter.
That was the time that we then knew that this had to be related to phenomena that was occurring on the Earth. And the only thing, of course, that we know enters into space is lightning.
But how could lightning on Earth affect the safe slot 6,500 kilometers up? When a lightning bolt tears through the air, it doesn't just produce light and sound, it also creates radio waves. If you turn on your radio when there's a storm nearby, you can hear them as interference. But if you tune in with an all-frequencies receiver, you can pick up more than just crackle. This eerie whistling is the sound of those radio waves after they've traveled through space.
What we've been listening to are lightning spherics. And these are emissions that occur from lightning hundreds of miles away that are propagated to us and are received in our antennas.
Green realized that these radio waves were the missing link. They connected lightning on Earth with the safe slot in space.
We never realized the importance that the ground is having on space.
In 2005, Jim and his team came up with a radical new theory. Less than a second after a lightning strike on Earth, the radio wave reaches the radiation belts. There, it interacts with the electrically charged particles, the radiation. It forces the particles out of the safe slot. The radiation is cleared, and the safe slot returns to normal.
We always had thought about lightning in the past, I believe, as a destructive mechanism. But I think we're discovering many of its beneficial factors.
If Green is right, without lightning, radiation would soon fill the safe slot. Satellites would fail, taking out many things we've come to rely on. Global communications, navigation systems, cell phones, and satellite television could all shut down. Life as we know it would grind to a halt.
If lightning stopped tomorrow, we would see a dramatic change in the way we live today. It's probably one of those fundamental parts of the equation that really contribute to life on Earth.
For millions of years, lightning has formed a part of our darkest visions and most terrifying myths. But now we're closer than ever to unlocking its secrets. And the more we discover, the more lightning defies expectation. Its origins may lie far beyond our world. It can take strange forms and create dazzling light shows. It is devastating, beautiful, and essential to life as we know it. The incredible journey of a lightning bolt takes us from outer space to the inner workings of the human body. Life and death, destruction and creation, all in less than the blink of an eye.